Hello my friends, welcome again to my video channel. Today we will continue our work on the Simpson260. In the first video we have seen there were some problems. So we can hope now that all electrical and mechanical problems are solved and we can start a first calibration check whether it is possible to calibrate this meter or whether we have other problems involved. Because it makes no sense, for example, to swap the banana connectors and to do a work in this direction when there is another big topic which stops the work immediately. So let's start. The first alignment check is the 50 microamp connection. I added a series resistor, 390 kilo ohms. This is a microammeter. So we can see the microamps. Full scale is 50 microamps, and with a voltage power supply I can now generate a current. I set it to 50 microamps. We see we have a deflection until we have here 50 microamps. 40, okay, we are a little bit above. We have to set the resistor R1 with the parallel resistor for exactly 50 microamps deflection, and R1 is the on the left side. Yes, this one. I can increase it to 50 microamps. A little bit touchy. Okay. 49.8. But you see, we can align it. We have enough overhead. $49.7. It's close to 50. By the way, the meter should be calibrated in horizontal position. I will calibrate it in vertical position. The mechanical zero is set. I do not do now a perfect calibration. I only check it whether it is in general okay. Next step is the setting of 1 milliamp. I need an input current of 1 milliamp. Go down and I will reduce this resistor a little bit down to 1 milliamp. I will choose 20K, 20 volt is 1 milliamp. I have now 1000 microamps, and full scale has to be adjusted with R2. This is a resistor, the trim pot we replaced. I will replace it by a new one, but in general we can see I can manage it setting to full scale 1 milliamp, this input. That's also okay. So we see this possible to adjust both points. I will recheck the 50 microamp setting. Again 50 microamps. Yes, 50.0. Precise, spot on. So both settings are okay. And that is for DC alignment. There are now other checkpoints for DC, and all other voltages, currents and so on should be correct. For example, this is input also for 250 millivolt. I will check it with 2.5 volt, but for this purpose I have to connect the meter in parallel. And now 2.5 volt DC measurement. It's a little bit touchy on the power supply. but I set it to 2.5, 2.488. There is a little bit less. Parallax error 2495. It's okay. Let's go to 10 volt. 234, 2.5 exactly between. That's okay. Let's go to 10 volt. Parallax error. And on 50 volt, that is 10 volt. Let's go to 30 volt. .8 for 30 volt. I think it's also okay. Now we can do the AC calibration, the check. Should I check the DC milliamp ranges? Yes, let's do the 100 milliamp DC check. The range is 500 milliamps. The meters are in series, of course. The power supply is current limited. Full scale is 500. It's a little bit more. But this is, I think, within the tolerance. Let's go to 100 milliamps. Yes, it's also okay. Now next step is AC calibration. Both meters are set to AC, 250 volt. I increase the voltage from my variac, isolation variac, of course. 350 volt, okay. A little bit too less. The indication is a little bit too much. 230, we have it 250. So I have to adjust R22 and R22, this one below. It is 230. Now I can increase to 250. Yes, that's okay. It's difficult with a variac to set the voltage precisely. Okay. Now we have it. And then we should go to the measurement range of 2.5 volt. I swap the connections on my variac. I have a low voltage output also with a low power transformer, low voltage transformer tapping. I go to 2.5 volt. I could generate this voltage also with a function generator. Maybe I will do it later. R25, and R25 is this one in the center here. This is, oh, it is set properly. Okay. Yes. 2.5. I have to look. This scale is 2.5. We can check the linearity of this scale. Let's go down to 1 volt. Whether we are here. A little bit less, 9. That's okay. It's a very precise scale, also for a low voltage measurement in the AC range. That's the reason why there are two different trim pots for setting of the AC scale. That's a good thing. Okay. We have seen that the measurement is okay for DC and AC. I didn't check the AC currents in the moment, but I think they're also okay. The ohm range is also. It's very important that the movement, the meter itself, is okay. I can set it with the parallel and series resistor, with these two resistors. We have been able to set the sensitivity with this one and this one, R1 and R2. This is important for the impedance and current sensitivity, and the rest is a result of the tolerances of the resistors, how precise this meter is or not. But in general, I think it's very precise. Okay. Well, what to do next? I will swap this trim pot here, buy a new one, and I see the resistance is rather small. Well, and the next step is to replace these connectors here by banana connectors. The board can easily be flipped out, only to unsolder this connection, which goes there, and this purple wire which goes through this hole to the switch has also to be unsoldered from this side, and it can be taken out. In this position it's also rather easy to replace this damaged 9-volt clip, which is connected here. Now we have access to the solder connection. We will take out these old inverse banana connectors, unsolder the component, and then I use a high sophisticated tool. You can also look at it in the other video from my first Simpson. The connections in the description below. And with this we can move it forth and back. Until it says no. And then with another sophisticated tool and some wood underneath, there's the other sophisticated tool. It should be possible to get it out. I take it out in all, totally 8, 2, 4, 6, totally 8, and replace them by my solution. I will show you. I've prepared a set of totally 8 of these BNC connectors, and there's a screw M4 with appropriate length. I drilled a hole in it at the end, you see, for the wire. This nut is needed to fix the this construction in the hole of the old banana connectors. They are fed through like this, and then this nut together with a lock washer is used to fix it like this, and then we can solder it. This is the first one. It shouldn't be too long, otherwise we will get in contact with the board, so this has to be short. This is maybe a little bit too short, some millimeters, but doesn't matter. It can be soldered, and then we can continue to the next one. Totally F8 for the big 2 connections of the resistive wire for the 10 ohm shunt. I made a different version. There is a slot in it on the top, you can see. And it is thick enough so we can slide it over the wire, and then the wire can be soldered in it also. All the banana connectors are now replaced by new ones. You can see them here as we want. Of course, we have no protection against touching them. We can touch them, and when we're measuring, for example, maximum 1 kV, 1000 volt DC maximum from here to here, then there is a danger that there is a high voltage on these connectors. We shouldn't touch them, but this is valid for all meters. When we have leads connected and connect them to high voltage, level, then we shouldn't touch it. So this is a laboratory instrument and not a instrument for common purpose. The wiring here is also renewed. Flexible ones, they were partially broken or in bad shape. This one again leads through this hole to the switch on the other side. I've checked the pot, which is bad, and with what we have replaced. But this one, by the way, I have ordered a new one, which is a bigger one. And I saw on the pot that there is a, maybe you can see it also, that here we have a damage. Don't know whether you can see it on the, here is a broken part, but I don't think it is broken. I think it's a burn mark. It was overloaded. And this would make sense because we have two resistors which have been replaced by the wrong ones, but they have been replaced, and the pot was also damaged. In the range 100 milliamps, the resistors were all damaged. I'll show you on the schematic. We had a damaged replaced resistor here with the wrong one, but this is a 100 milliamp track through this, and here we have contact in the setting 100 milliamp. This lever is here, goes there. This resistor was also replaced, or better said, the to be precise, this trimmer was bridged and this one was replaced, so it can be assumed that both were damaged, and it goes back to this, which is common. My assumption is there was an overload in the range 100 milliamps, this damaged, and now we have seen that the meter still is okay, but we have here parallel a VDR, a voltage dependent resistor, which are more or less two anti-parallel diodes. Maybe they have been overloaded. They are not shorted because we managed to adjust this to align it, these two resistors, but maybe it is open. Could have happened, so we have to check this. These are the two contacts of the meter. They are not connected, and this protective device is this one. This is a VDR. We can check it outside when this is no connection. Then we can apply a test voltage above it in the voltage range, so there is no other short, only the parallel resistor here, which is the 20K and this trim pot, but I think there is no problem. We will see the characteristic of these diodes or not. That's what I do. I use my component tester again on my scope and feed it to this VDR, and now we can look at the characteristic. It's okay. And now in connecting the probes, we see the result. The threshold voltage is about, we have 2 volt per division horizontally. I would say it's a third. It's okay, 0.6 volt or so, very steep. Yes, in both directions. So the protective diode, or VDR as it is, can be assumed as okay, and we can continue. By the way, it's a nice feature of the scope. Such a component tester is good for testing semiconductors. It's better than a go or non-go test with a multimeter to see the characteristic. It is not calibrated, of course, but to see something like this is better than a simple ohmic measurement with a multimeter. I do a short test of this pot. Setting is R times 100. This is 0. Not completely 0. 0 ohms should be aligned to 0. Now it is open. And when I will take another better lead for this purpose. And when I slide along the track, you see we have here good contact, 0. And when I come to the point where the brake is, suddenly nothing. Here we have contact, resistance, and here we have no resistance. And from the other side, vice versa. Same behavior. We can track the resistance. And when we're beyond this brake, we suddenly have no resistance. So indeed, here is a brake, as we can optically see. And there's another speciality. Here we have a bridge between the wiper. The wiper is removed, of course, and this lead. So it is 0 here. There's a bridge, and it is made in the factory. It's not a fault, it's made in the factory. This means this is not a potentiometer. It's only a variable resistor, we could say a rheostat, but not a potentiometer. And when I replace it, I have to do this bridge. Okay, this was obviously overloaded, as we have seen. Now we have to replace this 9-volt clip for the 9-volt battery. The new one is here. It is soldered to this connections. Here we have the corroded or disappeared clip for the 1.5 volt battery. We have to look for a replacement, but luckily the manufacturer has the same clip here, which is used to squeeze the 9-volt battery in this compartment. And this clip here is the same as we need here and can be used as a replacement. That's nice. Okay, I could say it's a very clever manufacturer, but I don't think that it's intended to have here a spare clip. And for the battery holder, we can use a different method. For example, I have prepared such a sheet of felt self-adhesive. I will bring it in here to squeeze the battery to hold it, but it's not critical. First step, solder this one. Second step, solder this one. But before, I have to clean the holder here from the signs of corrosion. The new 9-volt clip is in place. This contact is also replaced. And while I'm waiting for the new pot, I can start the cleaning inside. It's a little bit surprising. There's a lot of dust inside. Don't understand why. Was it stored open without cover, without the bottom cover? Because there are so many signs of dirt and dust in it. Here, everywhere. This cannot happen when the case is closed. Maybe it, and also on the top side of the board here, we can see there's also a lot of dust everywhere. Maybe it was stored open. Someone tried to repair it, took it aside and has forgotten it for 20 years. Maybe it happened. Don't know, but I will clean it. The contacts I don't spray with contact cleaner. I think it's not necessary. They look rather shiny. So the environment was obviously not wet. It was dry and not so cold. Also the pot here for the ohm setting, I hope it's okay. I can clean it later. So I will do some cleaning in the next steps. And for the places where I can't get access with the cotton with a Q-tip, I use a simple toothbrush. Good enough for the purpose. And for the rest I use a soft brush, dry. I don't use any water or any cleaning liquid, as long as it is not absolutely necessary, but it is only dust which can be wiped away, no problem. So it looks better now. Also here in the ridge, the slot, we should clean it. We can now start cleaning the front, the glass and the frame. There's also a lot of dust. To take off the glass, it's necessary to unscrew these 4 screws in the corner. And then the front panel can be taken off. The glass is off. Okay. It has to be cleaned. It's fixed with 4 clips. I think they can be taken off. It looks like it is glued also. I'm not sure. No, it's obviously not glued. It's only fixed by these 4 clips. Try to... No, not a good idea. Another bad idea, I think. I decided to leave the clips in place. The risk is too high to break the glass or to damage the clips or the plastic. There's a plastic pin coming out. And when I try to squeeze this clip up high above to remove it, then maybe something will break. And this would be not so nice, and I'm an idiot for the rest of my life. I simply clean it from both sides with clear water, that's enough. I use a window cleaner. Now this glass is very, very clean, free from any dust and fat and fingerprints and so on. Now I clean very, very carefully this frame outside, not to bring any dust into the movement, would be deadly. Only to remove the dust from this ridge here, from the corners. We have a very clean panel now. Glass is clean, no signs of any dust. So we can simply reinstall it with the screws. We also clean the screws a little bit. And now we have to check one important thing, that the pin which is used to set the 0 point, the mechanical 0 point, is in the right location. So we can now move the pointer to both sides. Okay. That's obviously okay. And now how to clean the case after a thorough cleaning with lukewarm water or some cleaning gasoline or so. I use car polish. It's for polishing cars. And apply it around this case on all sides. Wait until it dries out. Some minutes. That is the application note. And then try to wipe it off and see what happens. I think it looks rather good for its age. The handle, of course, was unscrewed. Be only careful here with the lettering. We only should use this cleaner very, very soft. The handle gets the same treatment. It also is now shiny. Good appearance. And now don't forget the cover for the battery and for the fuse. Same procedure for the 2 screws which fix the handle. I found a metal polish. It's good for bumpers and other chrome parts on the car, and it gets clean and shiny. Yes, that's okay. On the front I did the same. I removed the knobs. They can be taken off carefully not to break something, but there are no set screws. They're only fixed with some springs in it. There's also this big knob. Then they can be cleaned. Be careful not to wipe out the lettering, the white color. Only do a soft cleaning on the surface. Well, cleaning is done. A new problem occurred. There was a pin like this one, which stabilizes the board, and on the pin there should have been a clip to fix it, but the clip wasn't present. It was lost. Maybe someone took out the board very often and the clip was lost or damaged. I tried to cut a thread on this pin. When I did this, the pin broke off. So I decided to cut the pin flat, both sides, to drill a hole in it, 3.5 millimeter, and cut a thread in it, M4. As you can see here, very easy. And now I can use a screw, a nylon screw, like this, here and here, and then I can fix the board. And this can be undone very easily and it doesn't break. By the way, the case is not bakelite as it looks. It's called phenolic. It's a little bit more soft like plastic. It's not so brittle as bakelite. I don't know the chemistry behind, but it is a little bit soft. When I cut it, I've seen it reacts, and it is a little bit flexible. It's very good for this purpose. If you have a problem cutting M4 in it, M3 would also be sufficient, M3, but then you need a washer. No problem. Well, the new trim pot arrived. I will replace the old one, the provisional one, by this one, and then we can finalize the project. The new pot is in place. By the way, I ordered the wrong one. It's for an axis, not with a slot for, for an alignment tool. Okay. It was too late in the evening when I placed the order, and I don't want to reorder another one. I have to reinstall this bridge. We have seen this trim pot here has a connection from the wiper to this pin. So I have to add this connection also from here to here, or better said from the pin from here to here, to have identical situation, identical electric wiring. Otherwise the trim pot wouldn't work because the pin of the wiper isn't connected. Connection is only from here to here. The bridge is soldered in, and now we can reinstall the board. We should not forget this wiring to feed it through this hole and connect it to the switch. And here this tapping it for the 10 amp shunt resistor. Maybe it has to be reset to a proper value, but I will connect it in the original position and see during the calibration process whether it is right or not. It can be changed rather easily even when the board is installed, no problem. I placed in 2 batteries to check the ohmic range. They are also okay. For example, R times 100. Closed, 0 ohms, yes, that's it. Now I use a resistor 22K. Sorry, yes, 22K times 100, 200 times 100. When I go to R times 10,000, it is 2 2 and a little bit more. 2, 2. I hope it is 0. Yes, it is 0. And now 22K is 2, 2. Well, the ohmic ranges are also okay. Doesn't it look great? A black beauty, a black swan, looking perfect from all sides, as it should. It's one of the analog meters everyone needs who is working on electronics. Digital multimeters are very fine. I often use digital multimeters, but sometimes an old analog multimeter has advantages. I will not discuss it today. Best is you try it and then you see the difference and you will recognize the advantage of such an old analog volt ohm meter and of course amp meter. Now we are at the end of part 2. The Simpson260 is fully restored. Now I call it a restoration because it was sometimes badly treated, mistreated, wrong resistors, wrong wiring. Don't know exactly what happened. Anyhow, it's okay now. In the next part, in part 3, I will do a complete realignment and I will check the accuracy in all voltage and amp ranges and ohm ranges as far as I can do it with my equipment I have here, but I think I can do it. 1000 volt AC will be a little bit difficult. 1000 volt DC, I think I can generate it and measure it. Stay healthy, stay tuned. See you on this channel.